Hello again. Now we have a talk about quantum key distribution by my wonderful dad, Andy Simpkins, and his colleague, Rob Woodward.
Right, okay, so a quick introduction to QKD, a bit of an introduction to quantum-resistant cryptography, followed by what it means, or what it potentially means, for Debian down the road. So to start off with, this is going to be pretty much an interest talk, and then we're going to try and build on that of where we as individuals, not as Toshiba, but we as individuals think we need to go to be aware of what's going to happen at the point a functioning quantum computer of a large enough scale becomes available. So this is very much like the next talk on time t epoch. This is something for down the road, but that down the road is getting sufficiently close that we need to start paying attention to it now. So to start off with, I'll ask Rob to give us a bit of background into what we're talking about. Rob.
Okay, thanks, Andy. So I'm here as the quantum scientist being rehabilitated in DebConf. So yeah, nice to be here. And I thought we'd start with just a very brief introduction to Toshiba. I said this isn't intended to be a corporate sales pitch, but it's our first time here at DebConf, hopefully not our last, and it might be interesting to tell you a little bit about ourselves. So we've been based in Toshiba, in Cambridge, for a long time, doing R&D in quantum technologies. And then it's only really in the last few years that this has become an actual product. A lot of the R&Ds develop useful things, and we're now here in Cambridge manufacturing and developing products for quantum secure communications, which is the topic that we'll talk about today. So, what is quantum and why should you care? I think the word quantum is probably a bit like AI and machine learning. It's, I think, very overused. There's so much hype. You might get tired of it, but deep down there is something that's actually very useful there, and something that has a lot of potential to be used, communications, sensing, computing, across the board. And in terms of quantum technologies, people often talk about two generations. Quantum 1.0, we're all familiar with lasers, with transistors. This came out of the last century's worth of theory and development, using things like wave-particle duality, realizing that energy levels in atoms are actually quantized. And then when you have that understanding, you can build these new technologies, which we now take for granted. We're now approaching what some people call quantum 2.0. This is taking advantage of other ideas in quantum physics, things like superposition, entanglement, newer ideas, if you like, although they've been around for a long time, and now seeing how can we use these to build new technologies. And just in case you're wondering, if you haven't seen this sort of thing before, this is Google, I think it's Google's quantum computer. The actual chip is right at the tip there, and this is a big dilution fridge to get it down to sub 1 Kelvin temperatures. Now, I mentioned a lot of the ideas have been around for a while, so why now is a good time to talk about it. I think the last 5 years we've seen really huge progress here. So starting in 2019, you might have seen Google achieve quantum supremacy, also known as quantum advantage. That was the first time a quantum computer did something faster than a classical one. It wasn't useful, it was a sort of fairly arbitrary mathematical algorithm, but it was a nice demonstration of what could be achieved if you can have the right algorithms for the hardware and the right problems. And that really opened the floodgates. It was repeated by other companies in China, a chip company in Canada, and we're seeing very rapid scaling of the performance of quantum computers. So classically, we're used to Moore's law, the doubling of transistors or performance every 18 months, 2 years. In the quantum space, there's Nevin's law, a chap from Google, and he says that things are growing doubly exponentially. So again, numbers are much lower than classical counterparts, but really around now, we're seeing the heavy scaling up of qubits and ultimately performance. What does this mean? These things are very important. Quantum computers are not just faster. They're not going to replace classical ones. They also don't, contrary to the mass media and popular opinion, they don't just do everything in parallel. That's not how they achieve any benefits. What they do, however, is they let you do a new type of computation. So if you have the appropriate algorithms, you can get exponential benefits for certain problems, particularly things like optimization, and hence a lot of the excitement for drug discovery and other things like that. But there is a but. Yeah, sorry. See aforementioned slide about hype. There's some real problems that this could potentially open, as well as real benefits. Personally, to me, I think computing in a high-dimensional Hilbert space is quite far away from thermonuclear apocalypse, but that's interpretation. The issue is really that one of the things the computers with a quantum processor are good at is breaking, basically, the algorithms that we currently depend for crypto primitives such as RSA and elliptic curves. These are obviously used throughout the internet, throughout many of our Debian community approaches. Andy will say more about that later. And when I mean broken, technically what that is you're going from something that's computationally hard to solve exponential time, and you're reducing it on a quantum computer to polynomial time. So in other words, the assumed computational hardness is now not so hard, and therefore you can, in fact, factor a big integer with a quantum computer and effectively break that primitive. So the threat assessment now is that asymmetric crypto, so public key stuff that uses RSA, elliptic curves, etc., that's basically no longer suitable in a quantum-enabled world. On the symmetric side of things, so this is the likes of AES for encrypting data at rest, this isn't broken. There's no known attacks that can completely trivialize the problem, but the security is weakened. So the approach would be use longer keys with AES to get the same security that we have now in the classical world. And again, can we just ignore this? I'm talking about the future. I'm talking about quantum computers having enough performance to do this. You could just forget about it. And we'd say probably that would be unwise. There's an attack known as the harvest now decrypt later attack, which says that if you record all of the data that's sent in flight now, and you just wait until more power comes along computationally, you could then retrospectively decrypt that data and read the plain texts. Maybe for some stuff doesn't matter, but for things like medical data or government-level communications, where you have maybe 50-year lifetime, that's quite a long time to keep data private if you assume that quantum technology is going to keep advancing at the current pace. So in terms of solutions, there's two main approaches. There's a mathematical approach called quantum-resistant cryptography, that Andy will talk about in a little bit. There's also a quantum-based approach, which we've been pioneering at Toshiba, and indeed other companies have around the world too, called quantum key distribution. And I'll just spend a few slides telling you about that. I think if you work in cybersecurity or if you work in networks, it's interesting to be aware of this as a potential solution. So the basic idea is normally when you send data, often you don't think about it, but you're sending packets of light, long distances over fiber. That light is bright. So there's millions of photons being transmitted per second. In the quantum domain, we send single photons, because that's how you get access to all these nice, interesting phenomena like superposition, entanglement, etc. And the basic idea is that quantum key distribution, or QKD, gives you a provably secure method for deriving these keys. So to show the protocol very briefly, we have one node, this is a point-to-point link for simplicity. You're sending single photons across the link, and you encode information onto that photon. But you do so in a superposition state. So it's back to the whole quantum thing. It doesn't really exist until it's been measured. Now that means that if someone tries to attack your link, tries to measure that light, they effectively collapse that superposition. They alter the state irreparably so that at the other end, that can be measured as noise. And effectively that gives you a way of detecting an attacker based on the laws of physics, and therefore you can process out that potential leakage, resulting in a perfectly secure key you can use for encryption or whatever your desired application is. Now, I say perfectly secure, nothing is ever unbreakable. What QKD gives us is a provably secure method. So going back to Claude Shannon and information theory, it gives you a way of bounding the leakage using quantum physics and information theory. And typically we bound this to leaking one key in 30,000 years, or some sort of incredibly long time frame. So that's where the security guarantee comes from. I say, if anyone's interested in more of the optics and the physics, I'm very happy to discuss later, but for now we'll discuss more the kind of general concepts. So the way in which that would be used, normally if you're doing TLS, you have the client-server hello message, you establish your session key to use for encryption. In this case, you replace that handshake with pulling a key from the quantum box. So we have our 2 nodes generating keys, and then there's a REST API. It's an international standard now. It's supported by all the main encryptor vendors. You can just request your session key from the quantum hardware and then use that for encryption, be it AES if you want to use something which is currently quantum safe, or if you want to go the full mile, you can use something like the one-time pad, which is also known to be provably secure with no assumptions. I'll mention just very briefly, when people think quantum, I mentioned at the start that big picture of a cryocooler. You can get great performance with cryogenics. In the real world, maybe that's less attractive, particularly for data centers. So our approach has always been going towards practical systems and things that you can actually deploy in a normal data center. And what that looks like, this is a complete example system. So the main features being you take a laser, you can encode quantum states. It's very similar to how you would do so with classical communications. The main difference is that you stick a big attenuator on the end, take the power down from the bright regime to the single photon regime. At the receiver, you measure them, and then you also have something that I think is quite interesting if you're new to quantum technologies. Whenever you have a quantum protocol, you need a classical communication stream as well to support that protocol. So quantum comms is never going to replace classical comms. Quantum computers are never going to replace classical computers. It's that combination together which gives you the new functionality. And of course, when you're using optical fibers, you can combine everything together on different wavelengths. So it's still very compatible with existing infrastructure. And again, current range is about 150 kilometers commercially. In the lab, you can go further. And indeed, around the world, everyone's trying to push this to more and more reach. And our box is about 2U, so kind of very compatible with data centers. I'll mention just briefly the software side. We wouldn't normally talk about this, certainly in a physics conference, but I think for DebConf, it's quite interesting. From a software developer point of view, the software is really fascinating, actually, particularly things like error correction, which, of course, you need to do on any physical link. You can't really use things like forward error correction because the information doesn't exist until it's been received. So you have to come up with some other interesting algorithms there. If you're interested, one called Cascade is particularly promising here. That's based on repeated parity checking for smaller and smaller blocks. And then another concept coming from classical cryptography is randomness extraction or privacy amplification. And this is whereby you look at the statistics of your link and you say, I received, 1,000 bits. Based on the security proofs, I can get 500 secure bits from here that are perfectly secure. And then to go from that 1,000 bits of unsecure bits to 500 that are provably secure, you apply a randomness extraction technique, which distills the randomness into a smaller pool, but a more secure pool that you can then give to users for using as keys or indeed whatever application they might have. And again, these are both quite computationally demanding, so it's a very, interesting software problem too. In practice, a lot of people talk about this in terms of physics experiments. We firmly believe this is a practical technology, and we've deployed it around the world. Lots of trials with real-world users, so people like Orange, BT, JP Morgan Chase. One thing that's quite interesting is a lot of the big banks now actually have their own quantum team. Enterprise is certainly taking this very seriously, which is good. So to give you maybe a quick snapshot of what that looks like in practice, this is some work we did with BT. This was securing a link in Bristol between the National Composite Centre and the Centre for Modelling and Simulation. They deal with quite a lot of IP-sensitive things, and they wanted a better solution than the internet. So installing the box, you can see the network here. I won't go through it in all detail. The main thing to note is it looks like a normal network. That's the kind of point is, you don't have to rebuild everything. You just install your QKD hardware here. You pull the keys into your encryptor, and everything else, if you want to use firewalls, Ethernet switches, etc., runs as it normally would.
And I guess to show something else on that slide is if on the rainbow colour bits at the end, we're using exactly the same type of infrastructure. We're just putting the quantum signal on one channel. So this is something that you can deploy now without having to completely rip up and dig up the road and start to build a new network. You can deploy it onto existing infrastructure.
Exactly, yep. It's quite interesting, actually, because when you're trying to combine quantum and classical signals, the classical signals are millions of times stronger. So it's it's an interesting challenge to do that, but perfectly possible with the right optics and the right hardware. Again, you know, if someone in the physics domain tells you they built something cool, always ask them to show you it in practice, ideally for more than 1 minute. So this is a system running over about 6 months, fairly stable despite real-world fluctuations, people tripping over fibers, that sort of thing. And then extending this to the network scale, an interesting question is, well, how do you turn this single link into something that can serve multiple users, multiple sites? And the current technology is a technique known as trusted node relaying, whereby you relay a key hop to hop between all your links. It's a little bit like packet switching, if you like, but you're relaying a key rather than the packet. And we've used that to build a network in London. And this is really a prototype network for how you connect enterprise in London and real-world businesses. So in collaboration with BT, we've built this core ring network. And again, similar to classical networks, rings are good for redundancy. If someone drives a digger through here, you can reroute information the other way. And again, another approach from classical comms is the access network idea. So when we add customers, in this case, we've got people like EY, AWS, HSBC on board, we can spur off onto their networks, and then they can get back to the main ring and communicate with anywhere else on the network. So we see that as being similar to classically, a scalable way of growing this with time. One thing that I'm personally very interested in is how you can link the ideas from classical networking to quantum networking. Does the OSI model apply? It's debatable. People would say either way, because if you're going physical layer and then up, but you have to go back when you've measured something because that changes the information. There's some very interesting questions there. Others are proposing completely new stacks for quantum networks. But the main idea is you have your connected links, and then we can relay keys in the key delivery layer. So what that might look like, for example, is something like this. So you have the optics hardware on the lower level. You then have a key management system. It's a little bit like a router that routes the keys around your network. And then, of course, your applications can build on top of that, requesting the keys for encryption or whatever they might want to use it for. And I'll just mention that, I say, a lot of the encryptors from commercial vendors, this is one from Adver, but people like Talos, others have already supported this. There's a REST API that you can use. It's an ETSI standard. So if you buy a encryptor from most vendors and QKD hardware from most vendors, they can interoperate and be deployed without any specialist software and hardware now, which is beyond the actual boxes, which is good. And then my final slide, again, there's people here who I'm sure can say far more about this, but looking back at the literature, I think there's some quite nice analogies between the early days of the internet. So this is connecting ARPANET to a few other networks in the US. Actually, UCL's on this one, I think. UCL, so starting to connect to the UK, which is why I picked it. And this is the state of the UK's current quantum network. So we have metro networks in Cambridge, another metro in Bristol, and these are being connected together by long-distance backbones. So hopefully we'll see this continue to grow and also embracing other countries and different country scale things into the future. So thank you very much. That's the snapshot of the quantum approach. Andy, you want to tell you a bit more about the algorithmic approach to this problem?
Okay, so thank you very much. So quantum resistant. We've got this concept of an oncoming quantum computer, which, for want of a better word, is going to massively weaken, or indeed, in the case of the asymmetric cryptography, effectively consider our existing cryptography systems to be open. When is that going to happen? So at the moment, we've got a mathematically provable or information theoretically secure system in the form of point-to-point entropy delivery, the QKD approach. Post-quantum quantum cryptography, I'll get it right in a minute, is not yet mathematically proven, but then again, neither is our existing asymmetric cryptography. So we're not making the world a better place with this. What we're doing is giving us exactly the same level of security pre-quantum computer in a post-quantum age. When's it going to happen? Well, the NSA, our favourite three-letter agency in the United States, have mandated that all American agencies need to be considered to have moved over to quantum-resistant algorithms by the end of 2035. NIST and the NSA are due to produce a set of documents for which standards to be implemented this time next year. And the NCSC, which is the British equivalent, advise that you should be looking at picking a post-quantum system ASAP. So we don't yet know everything that's going to exist, but the Americans are shortlisting 4 algorithms, 1 for key exchange and 4 for authentication or signatures. Other organisations, pick your favourite agency, may recommend a different algorithm. That might be an issue for us as Debian, because which algorithm should we, if any, adopt? You might not trust a PQC algorithm. So we currently have people using elliptic curves, we have people using other standards. To start off with, you might want to consider using both one after the other in a hybrid key format, and that will allow you to have exactly the same level of security as you currently trust, because this gives you the only as good as the most secure. You can assume the other algorithm is completely insecure. So at the point where our existing systems are set up and it's all good, give it a score of 1 and treat the PQC as a score of 0. But at some point you might have to say, well, actually, we now trust the PQC system and downgrade the scoring for the existing setup. Again, that's going to protect against the harvest now to decrypt later, and it's also going to help protect against a suitable quantum computer coming on earlier than expected. What does that mean within Debian? These are my opinions. These are not those of my employer. Please note, change of slides. These are my opinions. So Debian uses PKI for all of our authentication. So that's apt. How do we upgrade a package? How do we deploy and push something new? And as far as I can see, apt depends upon GPGV, and part of that is libcryptg. DAC, I am told, is relying on a bunch of hashes, and DI using apt, and I'm not entirely sure yet what UDEBs are using. My guess is it's exactly the same structure underneath. So we need that for the installation images. So how do we fix it? Fix it? Do we need to fix it? I guess the safest thing would be to just fix the things that apps depends upon, and that will be introducing some PQC algorithm, some hybrid key setup is probably the right way. And that probably means that as a project, we realistically need to rely on the upstream releases of GNU-PG. I haven't gone through the release notes in detail, so I'm not going to claim I know the contents here, but my guess is we're probably going to have to wait for GPG 2.6 and hope that that has the hybrid PQC keys in it. We also require PKI to authenticate our developers and to authenticate against our existing infrastructure. So our keyring, our servers, our build boxes. And at the moment, we use Debian stable or old stable, or I think in some places old stable. What happens if we think we're going to enter the post-quantum age sooner than we can deploy? Are we going to be able to add hybrid keying to several previous releases? Or do we potentially want to consider how do we change our infrastructure so we can add PQC for authentication? And then there's finally the packages that depend on public key infrastructure themselves. So this is what our end users are using. Well, quite frankly, that's almost every internet-facing package in the archive. Now, as far as I'm concerned, I really don't care about that, because end users will adopt their packages. End users will depend upon a hybrid key or a post-quantum algorithm at some point in the future. But if we don't depend on it, we can't actually deploy to our customers, our end users, something useful. Now, OpenSSH version 9 tried to introduce hybrid keys, and they went in with NTRU. This looked like a good candidate, and NIST dropped that from their list a while back. So, it might not be the wrong algorithm, but it's certainly not one that NIST are currently advocating. But it at least shows that upstream of Debian, people are aware that there is a problem to come. So if we have a look at a timeline, we have a cliff edge. And at some point in the future, there's going to be a viable high-performance quantum computer. Now, that's going to be something that's going to be able to effectively render our PKI useless. And people believe that that lies between 5 and 10 years away. The optimists at 10 years, the pessimists at 5. So 5 years away, 2029. We're currently in bookworm. Ideally, 2025, we'll have Twixie, 4-key, game over. Debian as a project is not renowned for being especially fast at transitions. So we're 2 releases away from the earliest point where this might break us. If we do nothing and we're broken, at the very least we're going to have to rebootstrap our web of trust and restart our security from the ground up and start redeploying. So maybe we could start to consider doing something. So can we secure our infrastructure if we need to, and how fast can we do it? Well, assuming hybrid keys are the answer, and I think they are, we must add that to our existing servers. But our existing servers use stable, so does that mean we have to get everything in before said time? We probably want to run hybrid keys in parallel to our infrastructure. So we probably want to have this as an option. You could do one or the other. Don't depend. And then we could deprecate after we require support. Now, normally that would require multiple release cycles. How can we do it today? And given the way Debian runs, we can probably secure our infrastructure quickly if needed, but I suspect this is going to start a 2-year, 3-year, 4-year long flame war before we actually start doing anything. As for packages in the archive, again, typically we would introduce across several release cycles. Can we agree that this needs to be done? If we do agree it needs to be done, do we need to do this under a GR? Can we set it as a release goal? I'm hoping today that, I'm not asking for answers. I'm hoping to sow some seeds and start the discussions. Do we need to add PQC and hybrid keys into our systems? Again, require the use of. This is looking remarkably like the last set of slides. And then we can deprecate non-PQC, hopefully before the cliff edge is reached. Can we do it in 2 releases? My first guess would be probably not. What if we need to stagger by putting some of the infrastructure in place first the libraries, the dependencies, before we start with requiring the Leaf packages to support it. So that would be two release cycles on its own. If we're to achieve the goal of 2029, if that's indeed the project goal, we would need to add PQC support, we'd need the hybrid keying, and then we'd need to deploy that such that it's required. Now, back to our little train, we're here now, which means by Trixie we need both of those in. Ouch. That's what, a year and a bit away? Further 2 years, maybe 3 years to Forky. And at that point, success in the event that some sort of bridge. But of course, safe is with the usual caveats of all the things we don't yet know. So, questions straight away. I like this. Lots of questions. I thought this was going to happen.
Hello, thanks for the background about Quantum. I hope I can provide somewhat answers, actually. I pasted a link to the IRC about not my own work, but what Julian from the app team has been doing. And he's actively working on enabling to add new signature algorithms in a backwards compatible way to apt. And we already can add hash algorithms. So the repository side already has a proof of concept. Thanks to Julian, nothing of that is my own work. And I think he'd appreciate more review. So you have the link in IRC now.
Brilliant, thank you.
This needs to be done, and I do think it is, I mean, from Debian's usual timescales, this is a crisis.
Yeah.
Right? We can't afford to sit on this with our usual approach of letting this slide for another half decade.
No. I mean, it's the 5 years is the early estimates, but 10 years, by 10 years, that would be a crisis by Debian normal standards, right?
I have a more detailed question or observation or something. We use GNU-PG very heavily in almost all of our internal PKR use. And this transition plan involves significant changes to GNU-PG and upgrades to GNU-PG. My experiences and the experiences of other people I've spoken to about GNU-PG, both on a technical and a socio-political level, have not always been great. I think the biggest obvious risk here, apart from that we don't get our shit together, I mean, there's always a risk with Debian, but we have managed to do pretty well with the reproducible builds, for example. So if we all agree that we want this done, we can surely do it. But the biggest risk I see is that we have a critical dependency here on an upstream project that we might want to have a plan B for or something. I don't know.
Quick answer from Julian's wiki page. His proposal is to move away from GPG in a backwards compatible way, so having GPG signatures plus something replaceable.
So are you talking about a different underlying library structure, replacing GPG, or are we talking about patches into GPG to run alongside it?
I think it becomes more pluggable. So the release file format changes, and it gains a signature header where you can embed multiple signatures, and each of them can be produced with a tool of choice.
I know we asked this question in DebConf Kosovo, and I forget the maintainers, but Segoya PGP mentioned that it was on their roadmap as a feature to be added. So I can't speak where they're currently up to, but that might be another interesting avenue if OpenPGP doesn't.
I suspect adding additional algorithms to GPG is one large piece of work. To move away from using GPG entirely would be almost unfeasible, and patching or adding pluggable bits to it may well be a good start point. Today is just about, hey, this is a problem, guys. I offer absolutely no solution to this. I could potentially see a roadmap to what we need to do. I am not capable of implementing this. I can act as a point of focus.
So if post-quantum algorithms are in the new OpenPGP RFCs, then you can expect implementations like Sequoia to pick it up.
Yep.
Just as a data point, I believe RPM now uses Sequoia rather than GPG to do its OpenPGP verification. I believe the Sequoia project has interfacing libraries available to help that transition as well. I don't speak for that project, but I think that it would be, while not trivial, not particularly hard to replace, for example, our use of GPGV with an equivalent tool that used a project like Sequoia or some other OpenPGP library, if it turned out that the sticking point was GNU-PG upstream rather than OpenPGP in general.
Okay. This is actually surprising. I was expecting an awful lot more pushback on what we're talking about. So first of all, thank you everybody for taking this seriously. Where do we go from here? What do we do next?
Are there any post-quantum algorithms available on anything like a chaos key or a YubiKey or anything like that?
There are implementations underway. I believe Google has a project to implement some in a hardware token. The other thing that I think will change is the standards have been published in draft. Andy mentioned they were chosen earlier this year. The draft standards are now out. I believe they'll be ratified next year. So once the standards are officially published in their final form, or at least the first final form, that'll help to accelerate, I guess, the open community's adoption. Because at the moment, I imagine a lot of people aren't implementing or pushing ahead because they haven't been fully standardized yet. So I think next year we'll see a lot of movement in that area. But I think the other thing that's certainly a big phrase in, when you talk to enterprise people about this is the word crypto agility. The need to not just put your eggs in one basket, the need to support multiple algorithms or indeed multiple approaches should things happen that were unforeseen. So, for example, with PQC, Andy mentioned there's no proofs for that. Unfortunately, during the course of the competition that NIST ran, a lot of the algorithms that were submitted were either withdrawn or broken. Some when they even got through to the later stages. So there's always a risk with new crypto. Are there going to be vulnerabilities found that we weren't aware of? So again, crypto agility, hybrid approaches, that's a good way to mitigate that.
So, Steve.
Yeah, so there's a couple of issues I can see. You've mentioned already about a hardware token implementing new algorithms. I mean, I know from actually professionally just how awkward the bloody hardware tokens are
yes.
to work with. And, of course, lots of people have no idea what they're doing with them to start with. It'll take a while to rotate hardware out even once things have happened. Secondly, from looking at moving people forward onto newer versions of OpenSSL, which, of course, is going to be necessary, a substantial chunk of what is currently in Debian is, might now be buildable with OpenSSL 3. It's taken a very long time, but lots of them are still using deprecated APIs and for probably deprecated key types and Christ knows what. We're going to have, actually moving people forward for all of the packages that are trying to use TLS or whatever using OpenSSL is going to take a massive amount of work. We should all be trying to audit the packages that we're using, or especially the packages we're maintaining, and start putting up streams now rather than leaving it late.
Yeah, sooner definitely, Steve. Completely agree. This is effectively a call to arms. This is, hey guys, this is on the horizon. It's close enough we need to start doing something. In fact, it's possibly too close that we probably should have started sooner. It looks like some people have already started. But as a project, we perhaps want to look at making sure our own update mechanisms are switchable relatively quickly, to make sure that our own internal authentication processes work. And that, I guess, has to take precedence over what we are deploying in terms of what's inside a package, because that's how we are deploying those packages at a late stage. Absolutely, as you're saying, if you're maintaining any packages, making sure that they are capable of running the latest APIs is the right thing to do anyway, and potentially look at what's involved in adding in support when the upstreams happen. It sounds like we're not going to see anything until NIST publish their report next year, but we can at least start looking at how that infrastructure would plug together, and maybe start setting up a working group within Debian to start actually defining this.
Maybe one product that's worth mentioning, if anyone's interested, is libOQS, which is Open Quantum Safe. It's a consortium, I think it's led by Computer Evolution, well, University of Waterloo actually, in Canada, and basically they've taken a lot of the common libraries like SSL, OpenSSH, I think OpenPGP, and basically put a lot of the new candidates in as pluggable modules, so you can already try out, for example, libopenSSL with a PQC algorithm. The downside is there's a massive disclaimer saying not for production use, research only. So it's heavily caveated with for playing at the moment. But if anyone wants to, that probably is a good place to start.
Why don't we implement our own crypto? No, just kidding.
That's like Fight Club, isn't it? Rule one: never roll your own crypto.
In your first slides, the ones describing the how the network that you have in London today, how does the trust work there? You need to trust just the person in front of you, or you need to trust the whole network?
It's a good question. So the current trusted node relaying approach to networking, you have to trust every node that your packet, if you like, takes. So if I'm sending a key from one office to another office across London, I have to trust both the offices, but also the nodes of the BT network that I traverse. Maybe you're happy with that, which is fine. If you're not happy with that, there are future technologies that will replace that, so things like quantum repeaters, for full end-to-end relay, and also some other quantum protocols that can mitigate that. So in the future, that won't be required. But yeah, for now, you have to put trust in every node that your key hits. Yeah.
If you're lucky enough to be running your own campus network and you have dark fiber between buildings, you can implement your own point-to-point nodes, and it's up to you how you deal with your egress onto a wider network. But if you're wanting to secure to a third party, either you're in a point-to-point node to them directly. Again, this is back down to how the original internet, you had a network of your own systems and you talk to somebody else. This is just, at the moment, this key relay is about the only way we can foresee to enable you to get to an end communication partner, but the cost of that is you've got to trust the bits in the middle. As Rob says, there will be ways to improve upon that. There will be other technologies coming downstream, but they're going to be some way away before that's available. So it's a case of making sure your departmental security managers, your network teams, are aware of what there is currently, and get them to start asking the questions about what else they could get later down the road and decide when to jump. David, was it? Or Kurt? Who else has got the microphone? Yeah.
What latencies do you get on these kind of networks?
Latencies. So you can, again, there's many different ways of operating them. Often you operate where you can build up key pools. So, for example, we send, we clock at 1 gigahertz. We often build up keys at a rate greater than you would need to pull them. So in terms of latency, assuming you have a key buffer, you can get them instantly on demand. Latency is basically on your REST API call from one end to the other.
So if you've got an existing set of encryptors, they will rekey with an asymmetric system, either periodically or after a certain amount of data has been transferred. They'll then effectively go offline, they'll rekey and then restart again. This is a separate pool you pull from. So in theory, you could be rekeying more frequently than you would on an asymmetric key system. But this is a function of distance. If you're sending a single photon down a fiber cable, fiber optics are not superconductors for light, so they have loss. And if you're running 10 dB of loss, you're going to get considerably fewer photons out the end. If you send one photon at a gigahertz rate, well, you might only get a much lower receive rate at the end. And certainly after you've done error correction and privacy amplification, that rate is much lower. But whatever that rate is, that is your ultimate how fast you can rekey your encryptors. It looks like at the moment that you can do that faster than you would normally rekey for that link anyway, so you have some spare entropy at the end, which you might want to use for a one-time pad for more critical data protection. This is all about the same as a physical safe. Nothing is perfect forever. It's a matter of how long something is protected for. So maybe it's a case of you change your keys more frequently. You use a longer key to make them harder to break by brute force. Now that's the symmetric keys that your encryptors are using. This is just a method of getting new keys to those encryptors. A few more minutes if anybody has any more questions. Steve.
So going back to the implications for Debian, of course, we have traditionally had a very, 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 very slow key rollover process for, say, developer PGP keys. We're going to have to do better than that.
Yes.
As you said, key agility here. I don't have a great answer for that. For people here, yes, you all here, if we all generated new keys today, we could get them all signed and we'd be great. But obviously for every one person here, there's 10 or 100 out there who don't necessarily travel to events easily or who can't get new keys signed. I know the keyring maintainers have been working on better processes to actually deal with remote attestation and stuff. Please make sure you check on that and you help as much as you can with the coming, not apocalypse, bad word, but with the coming work that is needed, we're all going to have to help.
The other thing, could you use your old key to sign your new key?
Well, exactly. That's a way forward until we don't trust the old keys at all anymore.
Yeah.
So the nice thing with authentication and signing is that, well, I mentioned the harvest now decrypt later attack. That affects encryption because it's data at rest with long lifetimes. But authentication is a one-time transaction. So as long as you perform your authentication, your signature, your verification before that quantum computer arrives, that's fine. So I think that would be one way to do it.
Okay. In that case, I think that's everybody. No.
Your comment suggests to me that we need some kind of infrastructure that, and probably duplicate copies of it ideally, that collects keys and makes a record of when a signature was first seen, so that it can say, this new hybrid key was signed by this RSA key before date X. So that you can then look at that record and say, I'm happy to trust this key because the infrastructure says it was verified before the apocalypse.
I'm not really sure how to answer that, and I think I'm going to leave that to people who are better qualified in security than I will ever be. I am no mathematician.
I would hope that before we no longer trust the current classical keys, we have established hybrid keys that we have established some level of trust in as humans, and then we have replicated that signature. So we should not be in the post-quantum world relying on classical signatures that have been previously logged into a time oracle of some kind. We really don't need that sort of blockchain of verifications.
No, this has to happen before that point in time happens. Otherwise, we've got to re-establish our web of trust. Anyway, I do believe we're now out of time. If anybody wants to have further conversations of this, wants to talk about how QKD itself works, please do come and talk to us afterwards. Thank you very much for listening.